just a very brief recap of what we talked about previously. We basically took Darcy's law only. We saw that Darcy's law linked a flow velocity to a gradients of heads. We could write those gradients of heads for a simple one-dimensional element as a difference in heads, h1 minus h2 divided by a length. And from that we could make this little template 2x2 matrix which represented the conductance matrix for that element. And then we could use that as a template to represent a multiple system of elements which are stitched together end to end, just for two elements, the simplest system of relevance that we could deal with, and we could solve it for the appropriate boundary conditions. And so that's fine when we dealt with a one-dimensional system. It turns out that when we deal with a two-dimensional system, instead of being able to draw a single element, which is basically a brick with upstream and downstream elements, to solve two-dimensional problems, then we have to fill the volume in some way. And the simplest element that we could use is a triangular element, or we could use quadrilaterals, 2 and 3, with a similar idea that at each one of these nodes we'll have a magnitude of head, and we'll have a magnitude of flux. It's not quite so obvious what the flux is. I mean, certainly you can imagine what the flux is that comes across this surface, because it comes across this perpendicular surface as Q2. It's not quite so clear exactly what that would be if it's coming out of the vertex of a node, but we'll deal with that. So to be able to move from this one-dimensional element to two-dimensional elements, which might be triangles or they might be quadrilaterals. They could also be quadrilateral elements that are either made of triangles, or they could be separate quadrilateral elements in their own right. Then we need to be able to have a system that deals with this two-dimensional system, two-dimensional problem. And we can't do it just by using Darcy's law. We actually have to go back and use the expressions we had for conservation of mass. And so we don't necessarily need to revisit that because we have that expression already. I guess I don't need to do that. And the expression we have already is this one here, is equation 1. So equation 1 is just written in a slightly different way from before, but it's the conservation equation we talked about before. And the idea is that it defines mass rate in, if you remember, minus mass rate out. And equals accumulation, which is this term here. And this Q could be an applied flux. A distributed flux. So it could be rainfall, for instance. If you have a flat area and rain is falling down at 1 centimeter a day, then Q would be the additional amount of 1 centimeter per day that's added to the system. So that term has just popped in there apparently from nowhere, but we won't worry too much about it. And so what we're going to do is we'd like to be able to now take this conservation equation, and we would, which includes Darcy's law. So it's a conservation equation that has Darcy's law included. You'll remember if the conservation equation was just written in terms as a conservation equation, it had this term Vx in here, and we substituted Darcy's law for that term so that we had it written all in terms of one dependent variable. Heads on the left-hand side, heads on the right-hand side, and this is a prescribed magnitude. It's not something we solve for. And so that's the fundamental equation that we'd like to be able to solve. So what we can do is we can think about the geometry on which we solve it, and it's a two-dimensional geometry that we'll deal with. And we can think about the attributes of that geometry. And so the geometry is one that has a contour that goes around it. It's this classic kidney-shaped shape that is always represented in mechanics textbooks for some reason. It's always this curved shape. It has an area, which is a two-dimensional problem. It was a three-dimensional problem. It had a volume, but it has an area. And it has a surface that can be divided into two parts. One is the surface where the head is prescribed, and the other is a surface where flux is prescribed. And so you could imagine that, just if that's kind of strange to you, it could be that we prescribed our geometry from before, instead of being an upstream head which was equal to 25 meters, we could think about pumping out of the downstream part at Q equals 3.3 times 10 to the minus 6 meters cubed per second. I think that was the number that we calculated for for the flux. And so if we applied the flux here instead of a head, we'd actually get the right head value, because it's the same problem that we're solving. And so in this case, this is a head boundary condition which is applied, which is on this surface S sub A. And this is a flux boundary condition which is applied actually at a node, but it'd be representing this surface SP. So those are the two possible boundary conditions we can apply. The other thing we also know is that we know that as a requirement from Darcy's law, switching terms, we know that hydraulic conductivity in the x direction is equal to the gradient of head in the x direction. And we could also write this as a flux. This is a velocity, meters per second. This is meters per second. This is meters divided by meters. So, I know we used Qx as a volume flux before, but let's back off from that. And I guess we could also write the flux in the y direction is equal to Vy, which is equal to hydraulic conductivity in the y direction times gradient in the y direction. And actually we probably need a minus sign to be correct here, right? For the reasons we said before. The gradient is negative, so the flow rate occurs from high to low, and that gives a negative gradient, and so to balance it out mechanistically we have to include the minus sign. What we could do is, the additional thing we need to do is that instead of being able to define the flux in the x and the y directions, what we could do is we'd like to have a single value for flux. So just as before, we only had a single value at this node, a single value for head at node 3, and we would have a single value for flux that resulted. Then we need to have a single value for flux. And so we need to convert this value of a flux in the x direction and a flux in the y direction into a single value. And the easiest way to do that is to just take this little triangle at the boundary. And basically this triangle says that the amount of flux going in here is minus Qx. This. The amount of flux going in here is plus Qy, because they're in the positive directions of the x and y axis. So this is in the minus x direction, this is in the plus y direction. And so these go into here, and so if there's no net accumulation in here, the amount of flux that comes out of here has to equal these two amounts. And so what we can do is we can just take the components of this and write this in terms of the normal to the boundary vector. So we take this area here, this velocity, and we look at the dot product, the normal to the boundary vector, and this amount is the amount coming off for Qx, normalized for the amount flowing in this direction. So this is, if I draw a little box here, this is normal to this boundary. And this is the amount that is due to Qy. It's coming across this boundary. And so this is a single scalar magnitude. So we start off with a scalar magnitude on this boundary, a scalar magnitude on this boundary, and we combine them in some way to get the value which comes out normal to that value. And so that's Qn. So we have now a scalar value which represents the stuff that comes across this boundary. That's all we're attempting to do. And so these are just the angles of the inclination of this normal to the boundary vector relative to this. So this is alpha. This is this alpha. And so these are just direction cosines. So let's not get bogged down with that. It's not particularly important. So my usual approach to talking about the Galerkin method is that we end up with a very complicated expression, but I prefer to be able to explain in a big picture way and not get bogged down in the details what that expression is, because what it does is it results in a statement for the finite element equations that we can use always. And so the only thing that's important is the statement that comes out of it in terms of the matrix expression. So let's talk about it in big terms. So we have this domain. We have a boundary which head is prescribed on, where the head magnitude is equal to a prescribed head. HP is prescribed. We have a boundary on which there's a prescribed normal to the boundary flux. We define this prescribed flux in terms of Darcy's law and head gradients that exist at this boundary. And we do it because there's a single value for this, not a value in x and a value in y, but a single value normal to the boundary, so that we only have a single variable to be able to solve for. And so that's the essence of what we're doing now. And so the conditions that we have are that we have a governing equation, which is this, which we've talked about. Mass in minus mass out has to equal to accumulation. And this is an extra flux term that's added. So this is applied over the area of the system. We have a prescribed head, which is on the part of the boundary which we'll call SA. S is the surface, A is just the part where this is prescribed. And on SB we have a prescribed flux. And the flux, if it's prescribed, has to be consistent with the magnitudes of the gradients which will be developed in response to that flux. So if you imagine being on that boundary and taking a straw and sucking out at a certain flow rate, then the gradients inside the boundary will organize themselves so that they are consistent with the flux that you're pulling out of this. And so these gradients will develop that are consistent with the permeability magnitude and the orientation of the boundary, which would give you the right flow. They have to balance each other. So that's really what this statement is saying. I suck out at this flow rate, then it prescribes the gradients. If I double the conductivity of the system, then to get the same flow rate, these gradients will halve in that proportion. And so the Galerkin method is kind of a little bit complicated, but again, in terms of big pictures, it basically says this. It says that this governing equation has to be true everywhere within this area. This has to be true on the boundary where the head's prescribed. This has to be true on the portion of the boundary where the flux is prescribed. So what we could do is we could take this governing equation, which we rearrange by just subtracting this term off the left-hand side and putting it equal to 0. So let's subtract this off and make this equal to 0. So that's this equation here on the bottom. It's equal to 0. So this has to be true everywhere. So if it's true in one point of the area, then it's also true everywhere, and it's equal to 0. And so if we calculate it at every single point within that area, which is really what this integral is, then if individually at every single point it equals 0, then at all points summed together, they should also equal 0, right? That's the rationale. If we also multiply this equation by a factor, w, which we'll call a weighting function, then it still equals 0, right? At one point, it equals 0. You multiply the value at that point by 10, which is w. It still equals 0. And you look at all the points within the system and add them together. Individually, they equal 0. Collectively, they equal 0. And that's basically what this integral is. So we haven't violated anything yet. That's all we've done. The other thing we can say is that this expression for the behavior on the boundary, we could also rewrite, again, by rearranging this so that it equals 0, which then becomes this expression here. So this has to also equal 0 individually. If we multiply it by 10 at any point, it still equals 0. And if we calculate it at every single point around the boundary, which is where it's defined, which is what this integral is, and add that together, then it still equals 0. So we've done nothing to violate anything we've done so far, in that this expression is true, it equals 0 individually, it also equals 0 when we multiply it by any number, and it also equals 0 when we sum up all the values of 0, and likewise on the boundary. And so this is the expression that we'll use. We've weighted both of these by a so-called weighting function, w, that's what it's called, w. And that can be any number that we wish to choose. So equation 4 should still be absolutely valid. We have a PDE which has a second order term in it. So this term here clearly is, if we wrote it out in slightly differently, is something like d2h dy squared. So it's definitely a second order PDE. And so what we can do, is we can convert a second order PDE into two first order PDEs. Well, this starts off kind of as a first order PDE. And so we can rewrite this term here, which I guess is this one, right? Not the y. And so we can write this term, which we've pre-multiplied by this weighting factor, which we've integrated, and with respect to x and y, which are the directions of in our plane. And we can convert it into two portions just through Green's identity. And Green's identity says that we end up with a portion which is defined in terms of this weighting function, which is now here. So it's a first order differential and a first order differential with respect to w. So we've got rid of this dual second order derivative. And as a standard result, we also end up with this surface integral around the boundary as well, just as a standard result. Don't worry about it any more than that. So we've taken a second order PDE and converted it into a portion which is a first order with another first order term, and also a first order on the boundary. So we can do that equally because we have two of these. We have this one here, which we've done this to, and we have this one here, which we can do the same to, which is basically this. And if we substitute them back in, then this is the first part of this one. This is the second part. And the extra term that we have here has all of a sudden been migrated over here. This is this term here. So all we've done is we've basically taken these two first terms, we've converted them from a single second order PDE or operator into two first order terms and another one, and we've substituted them back into the expression. One of them goes here, which doesn't look like it's changed, but it has because this is dw, and one of them goes here. And when we do it for the second term, for the y term, which is this here, those parts just end up in the second place. this one here, and this one here. Just add it onto the other terms. And it's still equal to 0, so nothing's changed. So we've just messed around with this. What else? Well, we could also try simplifying it. If you look at, well, we could write out that the integral over the entire surface has to equal the integral over SA plus the integral over SB. This is true. It's just saying that if you look pictorial at this, is that the integral around this whole contour has to comprise individually the part integral on A and the integral on B. Nothing more than that. And if we rearrange this by subtracting this part off the left-hand side, then you end up with this expression here. That's all this is. That's where that comes from. And so, yeah, so what do we have? So this is over SB. This is over S. So in other words, this is the one that's over S minus SB. So in other words, this minus this has to equal this. That's what we're doing. So we're replacing these two parts here. If I draw a box around them, an integral that was defined in terms of S and SB in terms of one that's only in SA. And if you look down here, that's exactly what this is. So what parts do we, so let's kind of summarize a little bit. So this is our initial conservation equation, which was d dx kx dh dx, which we modified for this weighting factor. This is our flux that's applied over the area of the domain. This is the result of us doing this this other term here. This term here still exists, right? Which is this. And once we do this subtraction here, instead of having an integral over S minus SB, we have one only in terms of SA, which is this. This is this. And a flux term here that's left, which we don't care much about. And so that's the expression that we will now deal with. Again, it's a bit complicated, but we're interested in the final result. And so the important things to note, I guess, are noted here. This now is first order, not second order. Two first order operators, not a second order operator. There's a volumetric flux that's added here. The boundary flux is only defined on SA, which is this term here. And if you recall, SA is just the part where the head is prescribed. So this is SA. Oops. And we have a prescribed nodal flux condition on SB, which is basically this part here, QP, which is all that's left of this, right? This was our prescribed flux. This was the balance of the head gradients, which would be set up if we had our straw on the boundary and sucked. This would be the gradients that would be set up. But now we've thrown those away because of this little manipulation we did here. So that's our expression. So what are we going to do with this? So we added this one term which we never really fully defined, and it's this weighting factor, W. It appears here, it appears here, it appears here, and we made the case that this was just a number. We could apply at a point. It could be 10, it could be 100, it could be 5, it could be 0.1. didn't matter what it was, because you're multiplying something that is equal to 0, so it's still equal to 0. And so what we'll use for this weighting function is if you imagine an element to be joined like this. Imagine a quadrilateral element. Nodes 1, 2, 3, and 4. We'll talk about this later. We always number them counterclockwise, just by convention. 1, 2, 3, and 4, always. And so this is kind of a sideways view of a unit height at node 2 in this particular case. This is a unit height. And this is the pyramid it's not really a pyramid, is it? It's a prism that slopes up to this magnitude. You can see it better here. This is at node number 1. This is of unit height. This is the value of w. You can think of this as being the function w. And it slopes down to the other nodes and is identically equal to 0 at all the other nodes. This function that we'll choose has two requirements. It's equal to 1 at the node in question. So b1, which will be equal to w1, is 1 at the node in question, and it's equal to 0 at all the other nodes in the element. Those are the two requirements it has. It's important for us to realize that. So this is the function w1. This would be the function w2. It's equal to unity at node 2, and it's equal to 0 at the other nodes. This is the value at node 3, so this would be 1 equal. And this would be w3. Again, 1 at node 3 and 0 at all the other nodes. And likewise for the final one. And so what we'll do is we will replace this value for w, and we'll call it this function b. And b is the shape functions, so-called shape functions. And let's not get too embroiled in it, but basically the idea is it has to only satisfy this criterion. 1 at the node in question, b1 has to be 1 at node 1, and it has to be 0 at all the other nodes. If there are 10 other nodes, it has to be 0 at all 10 of those nodes. It doesn't matter what it does between those nodes. It could be linear, as it's shown here, or it could be some other shape. And indeed, we'll see that there can be some other shape. But that's the basic idea. And so this is kind of the idea, that above a particular node, the shape functions would be equal to 1, and they die away around those nodes to be equal to 0. So you can either define it within a single element, which is really what this is. This is one element that has nodes 1, 2, 3, and 4, in which case it individually has a shape function b1, b2, b3, and b4, all in that same element. Or you could also think it perhaps better in this particular system. Think about it as a whole series of checkerboard of these elements that are laid out, and you're interested in what the shape functions are around this node 12. Well, the shape functions would be equal to 1 at this point, and they die down to 0 at all the nodes that are some way associated with that central element 12, node 12. Right? These, like a circus tent, in other words. So that's what we're going to choose, and we've called them both B and W. I think we'll call them B from now on, I'm not sure. Yeah, B. So, call B. So, we're going to do two things. We're going to define what the value is of this weighting function, and we said this number can be anything we choose it to be, and we've just chosen it to be something specific, that it is these tent functions. And I guess the other thing is that we could also use it to define the magnitudes of the heads at a particular location as a function of the nodal values of those heads. So what this is going to say, and it's probably shown on this previous slide, the idea is that if we want to know the value of what the head is at some location, And so choose any location in one of these elements. Say we choose this point here. And this point, the same point would be the same in all of these, right? These are just depictions of the same element. So if we want to calculate what the value of h is at this location, one way to do it would be to use these mapping functions so that you take the value of the head at node 1 and multiply by the value of b1, not at node 1, but whatever the value of b1 is at this particular point. And so then we can take the value of the head at node 2 and multiply it by the value of b2 at this particular point, and the value of the head at node 3, which is h3, and multiply it by the value of b3 at this particular point, etc. And this would be h. We use the value of b at point 4, and the head magnitude of this. And if we add these together, so this is the value at node 1 multiplied by the value of this function evaluated at this point, value of head at node 2 multiplied by the value of b at this point, etc. We'll add it up. And so we can write this actually as a vector equation, a matrix equation. The values of these shape functions, the values of the nodal heads, and the other way to write it is basically this summation. Right? And so that's the other proviso that we're going to have for that. And I guess the other thing is, it perhaps now is clear the fact that we choose a unit height of this function at this point. Obviously, if this point was equal to the point where you wanted to calculate h, then this function would be the value of h1 multiplied by the value of b1 at this point, which is 1. So h1 times 1 is h1, plus the value of h2 multiplied by the value of b2 at this point. By definition, it's 0. So it's the value of h2 times 0, plus the value of h3 times 0, plus the value of h4 times 0. So by definition, it would return the value of the head at node 1. h1 is equal to b1 times h1. b1 is 1. So, okay, so that's really what we're doing. And so by way of saying that, we can use these mapping functions. These are what we've referred to, well, we'd call it W before, but now we're calling it a shape function, so-called shape function, that are described over the elements. And we can use it to map heads at the nodes to a value within the element. We can use it to map fluxes at the nodes to a value within the element. Or we can use it to define this rainfall amount at the nodes to a magnitude within the element. So we've basically done this. We've already kind of done this. And if we substitute these values of heads and fluxes back into this expression here, so fluxes, heads, they turn up anywhere else, I guess here and here, and do some manipulation. I'm not so worried about the manipulations. We end up with a really complicated equation, which is this equation here. But that's merely just by doing exactly what I just said. We take equation 8 and we substitute it into equation 7. And we get a very complicated expression out of it. And so rather than dwelling on what these are, you can probably follow exactly what they are. Let's look at the final expression, which is the most interesting and telling. And the final expression is this. It defines the behavior that we have for... Can we get both on the same page at the same time? Yeah, I think we can. So this is this part we had before. We've made these substitutions. And if you write it as a matrix equation, it's defined in terms of these components, which we'll look at. So this part here is this part just underlined. This part for the storage term here is this part here. This part for, no, that's not right, is it? Sorry, I jumped one. This is this one. This is just x. And what else are we left with? Whoops. This flux term on SB is this term. Running out of symbols to do it. And what else do we have here? And so this other part here is since we know that this magnitude is equal to this, and then so this term here is automatically satisfied by the fact that this gradient is set in place by any flow on this portion of A, which is the prescribed head boundary condition. So when we prescribe the head, it automatically satisfies this. So this part gets thrown away. And so the bottom line is that we have a matrix equation which looks like this. If we only look at the steady state part, if there is no transient part, then this drops out. And we're left with these components which represent behavior. This is a prescribed flux, which is equal to 0, then we don't have to worry about that. And this term here is merely equal to, the product of these is just equal to the nodal magnitudes of fluxes. And so the simplified form of this expression for the steady state, if I write it out, is equal to this integral times A transpose dA dx dy times head. These are vectors, is equal to QP. This is QP. And this is this. So we'll need these other two parts if we look at transient behavior, but for the steady state behavior we deal with this. And this is actually our conductance matrix that we had before. Not hydraulic conductivity, but actually the conductance matrix. You remember before that when we solved these, this problem, we had Q1, Q2 is equal to area times hydraulic conductivity over length multiplied by 1 minus 1 minus 1, 1, and then multiplied by the heads, H1 and H2. I'm not sure we ever did this, but we could have called this the flux vector. We could have called this the head vector, and they're related by a conductance matrix. And this is a typical, the finite element statement. It links the magnitudes of nodal heads with magnitudes of nodal fluxes by some matrix that we can define. And what we've done here is we've linked magnitudes of nodal heads with magnitudes of nodal fluxes with a matrix that we can define. A little more complicated now because it looks a bit different, but nonetheless it's a matrix that we can define. And what the individual components of this are, we've kind of glossed over that, is that these are terms that are the derivatives of these shape functions. So this is the derivative of the shape function. This is also a derivative of the shape function, and they're multiplied by a hydraulic conductivity in the middle. And so these terms that we have here, this is the derivative of the shape function, this is the derivative of the shape function, and this is Darcy's law, the hydraulic conductivity. And so the idea is that if we know what these shape functions are, we know that it's written down here, the A matrix is equal to the derivative with respect to x and the derivative with respect to y of the shape functions, which we've defined. And so if we know what these shape functions are, we can calculate quite easily what the derivatives are. So if we know what A is, then we know what this is, we know what the transpose is. If we know what the conductivity matrix is, then we know everything in this conductance matrix. But now it's not just done for this one-dimensional problem, which this is specific to. It's now done for both 2 dimensions, for other one-dimensional problems, for 2-dimensional problems, and also 3-dimensional problems. And so that's what we're dealing with in this particular case. Okay, all right. So if you, the stuff that we've gone through so far is actually shown in summary in this. So I don't know that we need to go through it again, but basically the idea is that we had this differential equation, capacitance term, accumulation, and we had this mass in minus mass out term is equal to 0. What we attempted to do was we took this differential equation, which is this, just written in this particular compact way. These are the same, right, of course. This terminology is just, P dot is just dP dt, change in pressure with time. So this is the specific storage term. We've called this S sub S. This term here is hydraulic conductivity, not okay. This is pressure, actually it's not, right? This is written in terms of permeability. So this term is actually permeability divided by viscosity, because Darcy's law can also be written as velocity is equal to hydraulic conductivity times head gradient, but it's also velocity is equal to permeability, not hydraulic conductivity, divided by viscosity times pressure gradient. Just an equivalent way of writing it. And so you'll see in this that this is just the same equation that we had before, written in a slightly different notation. So if you take this differential equation and you weight it by a function we'd called W before and set it equal to 0. So you set this equation equal to 0. You take it here, you multiply it by a weighting function, 5, 10, whatever it is, doesn't matter. And then it's equal to 0. If you integrate it at every single point in the domain and add them all together, it's still equal to 0. So this is still true. We map our pressures at nodes onto a pressure at a point using these weighting functions. We can define the gradients of pressures as this, which is just equal to the derivatives of these shape functions. I'll make it larger. So we use the weighting functions to map nodal values of pressure onto the pressure at a particular point in an element. If we want to take the derivatives of those pressures, so just in notation, P comma is equal to dP dx. And so we can just take the derivatives of these shape functions. Derivative, this is that dP dx is equal to dP dx. If we substitute this into here, then we end up with this. And this derivatives of these shape functions is just these A functions that we talked about before, just recently. And so that's that. And so now, what are we going to do? We take this expression here, we substitute in for the derivatives of pressure, which we have here, right? So that's this term here. This term is this. Yeah, that's it. We've substituted in, this is the same as it was before, which hasn't changed, except instead of making this the pressure change at a point, we make it the pressure change at the nodes multiplied by B. So that's just this substitution, right? So take this and stack it in here, and that's exactly what this is, BP. This is just P dot. So the underline means it's nodal values. It's doing exactly the same as we did on the handwritten part. What else do we do? We take this term and put it inside the bracket here. We take this term and also put it inside the bracket here. And that's what this is. And then we're left with the system equations that we had before. This is the storage matrix for the transient part. But if we're looking only at the steady state part, this is A transpose dA times the pressure is equal to 0. And so really it's the same as this term here. It's this, basically this, right? So it's just deriving a different way. Maybe it's more compact. Doesn't, it's not particularly important, I don't think. The only important part is that we end up with a system of equations that has a capacitance matrix. Which is this. And we have a conductance matrix, which is this. And we know exactly what the form of these matrices are. So we can use that in some useful way. Okay. What else? Right. So there's always an example to back these up, a one-dimensional example. So let's go through that. And so we could attempt the same problem we did before. This dam problem, so to speak. But what we'll do now is we'll develop the conductance matrix based on what we now know. And so what we now know is this conductance matrix has to take this form. And was it written that way before? Kind of, yeah, it was. So this is over the volume. So this would be a three-dimensional problem as opposed to over an area, but it doesn't matter. It's consistent with the other derivation. So now what we have is a physical statement that we can apply 1 dimensions, 2 dimensions, 3 dimensions, absolutely general. And so what we'll try and do is develop the conductance matrix for this problem. And it probably should turn out the same as it did in the simple way that we did it. It shouldn't be any different because we're not really operating in any different way. So again, let's do this. Let's take an element that's going to represent one of these. And this element is going to be a template, which is this. It's going to have 2 nodes, nodes 1 and nodes 2. At these nodes it will have a head at node 2 and a flux at node 2, a head at node 1 and a flux at node 1. That's our nodal variables. This is our local element of length L, cross-sectional area A, and hydraulic conductivity K. And we can take it as a template and we can put it in turn on this location and this location, just as we did before. Probably not very challenging to do that because we've done it. But what we'd like to do is be able to derive the local conductance matrix for this using this new expression that we have, because it's a universal expression that we can use. So what do we need to do to be able to do that? Well, we know that specifically we have 2 relationships that we need to deal with. We know that the important relationships are that the pressure at any point is equal to the product of the shape functions multiplied by the nodal pressures. And when we're looking at heads, defining in terms of heads, it means the head at a point is equal to the shape functions multiplied through by the nodal heads. So these are equivalent to each other. And we also know that the gradients of heads, if you just take the derivative of this, is equal to the derivative of the shape functions multiplied by pressures, nodal pressures, which is the same as the derivatives of the heads is equal to the derivatives of the shape functions multiplied by the heads, nodal heads. And so the reason that we can do this, of course, right, is that the values of the pressures at the nodes are only at the nodes. They don't exist in the element. The nodal pressures exist only at the nodes. And so we can't differentiate them. They're a single scalar value. The shape functions, by contrast, have a value that changes over the element. It has some slope to it, right? Because we remember we defined them in terms of this little picture here. And so the shape functions clearly have some value as they go across it. And actually, if you think about it, if it's a uniform plane that goes over the element, the derivative of that plane is just going to be a constant, right? Constant gradient is a y equals mx plus c. You take the derivative of y equals mx plus c, dy dx is equal to just m, right? It's the slope of that plane. And so in some cases, if it's a uniform gradient, then the derivative of that gradient will just be a constant. And so when we look at this matrix here, this term that we have here is actually what we've called A in this expression. Here. So the bottom line is that we want to be able to calculate this expression. We need to know what the A matrix is. And so to get the A matrix, we need to know what the derivative of the shape function is. To know what the derivative of the shape function is, we need to know what the shape function is. So we have to choose one. We said that the requirements for a shape function were that it would equal, well, let's go back on that, would equal 1 at the node and point and 0 everywhere else. But let's not deal with that for a while. Let's use another way of doing it. We know that between nodes 1, where the head is equal to h1, and node 2, where the head is equal to h2, the simplest variation in head is just going to be a linear variation. This is the equation of that. The head at any location along that line is equal to h1. So in other words, if you just draw this across here, this is h1, plus a magnitude which is the difference between h2 minus h1, which is this height here, scaled by the length. If x is equal to 0, in other words, if this point is equal to here, if this is x, and this is L, when x is equal to 0, then it returns the value of h is equal to h1. When x is equal to L, this is equal to 1. h1 minus h1 is 0, so the value of h is equal to h2. And you can see that anywhere between there, it just gives you the scaling factor. So this is the equation that we'd like to use for this so-called shape function. And so we have everything now we need to be able to construct this. We have a shape function, which we've defined, which actually just gives us this variable. How do I do this? I can't remember. Yeah, okay, we don't actually use it quite that way. The other way to do it would be that we can just calculate if we know what dh dx is as a function of this shape function, then we should be able to calculate what this A value is. So let's try that. Here we go. This is the expression we want to calculate. It's a function of a volume integral. Our system is much simpler than that. It's an element that looks like this, where it looks like this would be the x-axis. This would be, I want to do it the right way, so I'm going to be correct about this. So this would be y, z. Just to get a right-handed coordinate, this would be y, and this would be z. And so you can write, for instance, the integral of anything dv would be equal to the integral dx, let's do it backwards, dz, dy, dx. Integral dx dy is equal to the area, And so this is just equal to the area times the integral dx. Right? So that's where this comes from. dv can be transformed into dx and an area, nothing more than that. And now we have to figure out exactly what these terms are. This is our hydraulic conductivity in the x direction, which is just a single value. The A matrix is the derivatives of our shape functions, but it's also equal to dh dx is equal to A times h. Right? That's the other definition of our A matrix. So if we know what the variation of h looks like over the element, we could do this differentiation. We'd have an expression for this, and we could try and figure out exactly what this A was as a function of that. So let's do that. I guess I've done it a different way. Let's do it that way. So let's take the derivative dh, which is this. Sorry, didn't need to underline it, shouldn't be underlined. So what is that? The derivative of h1, I guess we lose we lose h1, right? So if we take the derivative, we lose this. We take this, we have h2 minus h1, which we keep. And the derivative of x over L is just 1 over L. Right? And so this, if you like, is equal to, we could rewrite this as 1 over L h1 h2 and what would be the terms? This would be minus 1 and this would be plus 1. So this is the derivative of this expression here. It's equal to this. If we just rearrange this in a way that's useful for us, then this is the change in head with location is equal to this, and then this is our nodal value of heads, and this by definition is our A matrix. So we needed an A matrix and a transpose of it. We needed a D matrix. We have all of those. So now we can just start putting it together. So if we do that, then let's make this. And so A transpose, this is A. So the transpose of that is just 1 over L minus 1, 1. So it's just the transpose of this. So this is A transpose. This is the value of K. You go up to the top of the page here, right? Sorry, this is D. Which is this. And the value of A, which is this, is just this. Which is no different from what we had here. So this is A. And if you multiply these scalars, you get hydraulic conductivity 1 over L, 1 over L. So this is hydraulic conductivity over L squared. We have the A outside the bracket, outside the integral, which is this. And we just have the remaining term is minus 1, 1 multiplied through by minus 1, 1. And as you remember, the product of this is minus 1 times minus 1 is plus 1. Minus 1 times plus 1 is minus 1, etc. And the final term that we're left with is, we still have an integral, right? We haven't lost this integral yet. It's between node 1 and node 2. The length of the element is x equals L. And so with this, the integral of this is just the integral of the individual components. So the integral of this is just AK over L squared, which is this. So if you take one of the terms, which is just this is just dx, then, why don't I write it out? So A, getting bogged down in minutiae, I guess, but that's okay, is the integral of 1 dx, which is equal to between 0 and L. The integral of 1, of course, is just x, right, which is equal to a kx over L squared multiplied by x evaluated between the limits of 0 and L. X between the limits of 0 and L is just L minus 0. So L minus 0 gives you an extra L on the top to counteract this, and so you lose the L squared because you have this term here. And if you do that for the other components, you end up with something that's very familiar, which is just equal to these individual components. And so, not surprisingly, maybe, we end up with exactly the same relationship we had before, which is the conductance matrix. But we're ahead of the game because now we know not only how to do it for this one-dimensional element, which we already had the solution for, with a very simple shape function. We could also make elements with much more complicated shape functions with multiple nodes in them, for instance. Elements we could make that instead of looking like this, with a node at each end, we could, if we wanted to, make one-dimensional elements that looked like, oops, don't mean this, had multiple nodes in them. So a node at the end, a node at one end, maybe a middle node as well, if we wanted to. And we're also in the condition, in the situation now, that we can put together elements that have two-dimensional behaviors, because the expression that we have is entirely general and allows us to do that. And so what we can do then is we can solve problems in more complex ways. I didn't want to destroy my great timing, so what we can do is we can mess around with some things. So that's the main point for this, is that we're now able to make these conductance matrices which can be applied uniformly in any geometry that we wish, 1, 2, or 3-dimensional, any shape element that we wish. All that changes will be the kinds of shape functions that we use to make them. And the shape functions, I guess it may not have been quite so clear, but I'm looking for a place to draw this. Yeah, let's do it here. So we made the point before, and I haven't actually violated it. We made the point before that the definition of the shape functions should be that they equal 1 at the point in question, but they equal 0 at every other point. And so what we did in our particular development of this element may have seemed a bit strange, but it could be represented in the same way, right? So if you have a shape function, for instance, that looks like, can I do it underneath there? No, I won't do it. I'll do it to the side. So if you wanted something that looks like this, where this is H1, and this is H2, which we had before, right? So that's basically what this is, right? H1, H2, separated by some length. This is L, this is 0. You could do it as a straight line that looks like this, but the other way you could define the shape functions could be like this. See if I can draw this properly. Not very well. Almost. This would be B1. This would be B2. And the expression would be that the head at any particular point is equal to B1 times H1 plus B2 times H2. These now satisfy the value that, well, it's not quite, if this, instead of being, yeah, all right, pretend that this isn't, that's not, yeah, okay, that's not quite right. So I'll draw something above it, because that'll make more sense. You could actually do it like this, where this is height 1, height 0, this is L, this is 0, this is B1, this is B2, this is also unit height, this is B1, this is B2. And then I guess it's useful to draw it like this, because if you think about it drawn like this, if you add these two effects together, you get this dotted line, right? You can probably show that geometrically. But in this case, the shape functions would be that the head at any point in the element would equal to be the value of the shape function times the head at node 1 plus the value of the shape function 2 times the head at node 2. And so you can very simply show that's true. So if you look at this point here, what's the value of head at this point? The value of head at this point has to be h1. So b1 is equal to 1 at this point. So this would be 1 times h1. What's the value of b2 at this point? It's clearly 0. 0 times h2, which is equal to h1. If you look at this point, you get the similar result, the opposite result, I guess, is that at this point, the head is equal to 0 times h1, because the value of b1 is equal to 0 at that point. The value of b2 is equal to 1. And this clearly is equal to 2. And so if you take any intermediate value or value intermediate to that, you'd find out that it would result in the value which is on this line, which would be the same as the value which would be here. It's exactly the same. So it's kind of cool. If we have 5 minutes, which I guess we do, the other way so the idea is that what finite element methods do is they compartmentalize everything at the level of the element. You define this template for the behavior of a single element, and then you just assemble it into some big global system of equations to be able to solve it. And so that's why the elements can be quite versatile, because you can mix 3-noded elements with quadrilateral elements with 9-noded elements all together in the same mesh, if you can get them together. And then you can solve them just by using relatively straightforward coding techniques. So the other thing that I have floating around, which would be kind of fun to use, would be, if I can think of where it is just this little code that I have. And if I can find it, it's here. You have this on the website, and you can download it should you so wish. I think if I click on this, it should open up. So this is FreeMat. It's a free version of MATLAB, or a public, a GNU version of MATLAB. And it runs a little code that I've made that is called EGEFEM. And what is set up here is it's set up in the same way that any big commercial code would run, but it's really an instructive tool more than anything else. And so if you have MATLAB, or if you have FreeMat or some emulator, you should be able to run this. And what is put in here is, that's useful to look at this element subroutine. So what happens is it localizes everything to a single element subroutine. And the idea is that within this element subroutine, it does the calculations that you'd need to be able to produce exactly this matrix here. So in other words, if you think about what this is, the idea is that it will take the information into the subroutine, and you can see exactly what that is. It needs information of the x-coordinates of the beginning and end point of the element, x1 and node 1 and x1 and x2, or the x-coordinate of node 1 and the x-coordinate of node 2. It needs to know what element type it is. It needs to know the hydraulic conductivity. It needs to know the area. It needs to know the capacitance if it's a transient problem, and it might need to know some other properties. And so what it does is it gets that information, and if you look at this, what's this? Coefficient is equal to the cross-sectional area, uppercase A, times the conductivity, K, divided by the length of the element. The length of the element is just the difference between the x coordinates at the two ends, the absolute value, so it doesn't get negative. And then it puts together a conductance matrix, which is this coefficient, +1, -1, -1, +1, which is exactly the expression we have. And so it puts this in a single element subroutine. It visits that element subroutine as it cycles through every single element you have in your mesh, calculates what the stiffness conductance matrix is, puts it in a global conductance matrix, and solves the problem. And so this is just a little problem set up to be able to solve the problem that we have. Remember the dam problem? Node 1, 0, 0. Node 2, 10 meters along the dam. Node 3, 10 meters extra along the dam. This is the code for the element. It's a one-dimensional element for flow. The 1 is for one-dimensional element. It's just a terminology I dreamt up. The conductivity of element number 1 is 10 to the minus 6 meters per second. The length of element 1 is cross-sectional area. It's 10 high by 1 into the page. So the area is 10. The other element is double the conductivity and the same height. Element number 1 has material number 1, which is this one, which is the downstream element. It has the left-hand node is node 1. The central node in the system is node 2, if you remember. I guess I could draw things behind, right? I can move this over here. Remember, it looked exactly like this. This was node 1, node 2, node 3, if you recall. So this is element number 1. We use Roman numerals for that, if you remember. And this is the left-hand node, the right-hand node. Element number 2 uses material number 2. The left-hand node is node 2. The right-hand node is node 3. It's here. It puts the boundary conditions in here. 1 defines a prescribed head. 0 defines a prescribed flux. Head prescribed at node 1. Flux at node 2 in the middle, which is 0. And head at node 3. The magnitudes of those heads are 20 meters at the left-hand side. The flux magnitude is 0 in the middle, because what we said before about inflow from one element being the outflow from the other. And the upstream head is this, 25 meters. And I think if we run it, we should get a result. Didn't run. Okay, let's try it again. That's because we're running this. We need to run the executable. Run the executable. What do we get? If I look at this, well, you see something's good at the bottom anyway. All the information, it kicks out all the information, but I guess the one thing you can see is that it calculates the local conductance matrices. One is here, which is 2 times 10 to the minus 6, plus 2, minus 2, minus 2, plus 2. There should be another one. So it goes, this is the downstream one, is it? So it calculates the downstream one, and then it puts it into the global conductance matrix in the top 2 left-hand portions. It calculates the one on the right, which is double the size and is double the magnitude of the conductance. It adds it into the global conductance matrix, these terms here. Right? And then it just puts together the vectors, and then it solves it. And so the results that come out are that the only variable that's a free variable is the middle head, which is 2370 over 3, you'll remember, which is this. We then take that head value, we substitute it into the matrix, and we calculate what the, well, actually we don't need to do that. We've calculated what the only unknown head value is. So we can put it with the other head values and we have the whole suite. Once we have that whole suite of values, we can multiply it by the conductance matrix and it gives us the fluxes. The fluxes come out to be minus 3.3 times 10 to the minus 6, 0 in the middle, even by calculation, and the opposite at the upstream. And so it just calculates it. So it's not really, certainly not a production model by any stretch of the imagination, but it is an instructive model we'll use in this class to be able to think about the data, simple data structuring and methods that we use to be able to solve these systems. So that if any of you ever want to write these kinds of codes or have to write these kinds of codes, it'll be self-evident.